The goal of Advanced Manufacturing Lab 1 was to familiarize ourselves with the interface and how to control the robots. The specific objective of this lab was to use the suction cup end effector to grab a block at a predetermined location. The challenging parts of this lab were familiarizing ourselves with the application used to control the robots, as well as the protocol for homing the robot and setting it up. Completing this lab set us up well to continue on to the tasks in Lab 2.
Lab 2 is the longest one of the 3 labs of advanced manufacturing, and many techniques and steps involved in this lab are also replicated in the final project. The main activities in this lab include conveyor belts, I/O communication with the conveyor belts, image acquisition, image processing, and feature matching, calibration that allows the transformation between image and physical coordinates, and other vision-guided image processing. The team started with a conveyor belt with blocks on it and an IR sensor on the side. The sensor sends out a signal when it detects a block at a specific location, which acts as the input to the program. A Dobot arm is programmed to reach to that location, pick the block up, and drop it aside, which acts as the output of the program. The I/O communication uses branch structure to decide when to send a signal and when not to. Image acquisition is another key part here. A camera is placed above what the team called the operation platform to capture and send images to the Dobot machine. The team studied the use of fast matching for feature recognition. The machine takes a picture and the teammates select and label the part we want on the image. And this sample is called feature template, and the program will try to look for similar items that appeared in the camera's field of view. After the fast matching, the machine knows, so there is a desirable feature there, but it needs to know where the feature is in real-world space so it can command the arm to move that point. This is achieved by calibration. The team placed a calibration platform on the operation platform and took a picture of it, and then we replace the end suction cup with a pen module and hover it on specific points on the calibration panel and record the corresponding robot arm coordinates. By entering these coordinates into robot program, we teach the machine the correlation between what it sees and where these features are in physical space. After the calibration, we can add modules to ask the machine to find the distance between 2 points and the path between them. In Lab 2, there are also vision-guided image processing techniques involved, such as color extraction, image morph, and blob. Color extraction uses the RGB values to filter out certain colors in the image and convert the image to a grayscale. Image morph and blob are modules used to reduce noise and make the image smoother at the feature edges, so fast match can use better quality grayscale images to make feature detection easier. And all these techniques are useful in the final project.
Lab 3's objective was split into 2 different main objectives. The first objective was to design a flow that would allow 2 different Dobots to pass a cube from one end of the table to the other autonomously. The second objective was to have a single Dobot fit square puzzle pieces into the correct slot. The setup of the first objective involved 2 separate Dobots mounted to conveyor belts that were deemed either sending or receiving, 1 foam cube, and a handshake circuit. First, we needed to understand the conveyor function in the Dobot software. Using the conveyor belt command, we would set the motor speed to 3000 and enable movement. This block would then be attached to a wait time block which lets the motor run for that set time. Then it finally runs into another conveyor belt block that's disabled to stop the movement of the Dobot on the conveyor. This would be the basic flow of getting the Dobot to move on the conveyor. Next, we integrated the handshake circuit in the flow. The circuit allows the 2 Dobots to communicate with one another. This works by having the Dobot 1 send a signal, which is then sent to Dobot 2 to perform the next action. The sending robot would have a flow composed of the basic conveyor movement flow to an I/O function, to an I/O output, to a wait time, to an I/O output. This flow will pick up the block using similar methods we used in Lab 2, move the block along the conveyor, and place it in the predetermined location. Once this operation is complete, the I/O output block sends a signal to the receiving Dobot, which will then trigger the receiving robot to then engage and complete the objective. The receiving robot has a similar flow to the sending, with a minor difference. The second objective involved using the object recognition features in Dobot. The setup for this part was one Dobot, a camera with a top-down view, and the puzzle with pieces. As we can see in the flow, there are some new blocks we haven't seen before. These are fast matching, shell module, and the calibration transformation. First, the calibration transformation block. This block was used to give coordinates to the Dobot in relation to the camera. Since the Dobot is not in a fixed location, the Dobot needs to be calibrated to the space within the camera's view. This is done to give a coordinate system in relation to the Dobot itself in which the Dobot can accurately move to. This was done using the pen attachment and checkerboard. 9 corners positioned on the checkerboard are recorded and made into the calibration file. This file will give us our coordinate system. Then there is the fast match block. This block is used to identify the pieces of the puzzle from the other surroundings. This block receives an image from the camera, then looks for the pieces in that image. It looks for the piece with the template we have created. This template is a snippet of a single piece, and the Dobot will try to find objects similar to it in the entire photograph. Using only one piece helps distinguish from the other pieces in the one image. We can then change the match score of the template, which either makes it easier or harder for the Dobot to declare if that object is a match. Because of the general shape of the piece, it can be set pretty low. An area is drawn on the fast match block where the Dobot will look for these objects that match the template. Another fast match is created for the holes of the puzzle using the same method. Then we have the shell module. Its job is to correctly orient the piece so it fits into the slot. This allows the robot to correctly place a piece no matter how it is laid down. Using similar movements we used in previous labs, the flow is now finished. The Dobot then looks in the area where the predetermined pieces will be. The Dobot picks it up and correctly orients it so it can fit into the slot, and then places it. For the piece to fit into the slot perfectly, a very good calibration file and accurate template for the fast matches are needed. It takes a lot of minor adjustments to achieve this.